Okay, so here we will start to use the definition of the, yeah, I mean the equation we just derived to find some expression um, of the potential due to different structure. The first one is the potential due to a charged particle. Okay, so yeah, so here we assume that we will try to find the potential due to this bottom charge, and then of course we also have a test charge there. And yeah, so here we try to apply the equation we just have. So we f minus vi equals negative integration of e dot ds from I to f. Okay, so here, yeah, so here, let me see. So yeah, so here we will consider this is the initial point, and then the final point is infinitely far away, which is the final point. Okay, and the path will be from this direction to that direction. So this is ds. That's why it shows ds pointing upward. Also, E field is pointing upward because this is a positive charge. So along this axis, E field is pointing upward. Okay, so here we already know that E dot ds is like this is our axis. This will be our axis. So we just make it like ds to be dr, and then E and ds points to the same direction. So E dot ds will be like E times dr. And then okay, so here we consider this is the r axis. This point will be from r, or maybe let me see. So here it's just write it as a capital R. So you just consider it to be capital R first. Finally, we just change it back to small r. So because we have dr to be the r axis, so just we don't want to change this variable. So we just keep this small r and then make this lower bound to be r. Otherwise, this is small r, this is small r. You cannot distinguish which is which. Okay, so this is capital R. The final point is infinitely far away, so this is infinity. Okay, so here we have a negative integration of E times dr, and then R from R to infinity. Okay, so in chapter 22, we already know that this E field should be this K times Q over R squared. So what we have get in chapter 22, then we can just plug in this expression into there. And also, we can also set Vf to be 0 at infinite far away, just as what I mentioned in the previous hour. Okay, so and also Vi to be V. V is what you want to find. So in that case, you plug in Vf to be 0, Vi to be V. So on the left side we have 0 minus V, and then we plug in this one to here. Okay, and then you can see this is dr. So all other variable other than r can be factored out. So we will have q over 4 pi epsilon naught, going outside. Here we also have a negative sign here, and then integration of dr over r squared. So we have r squared here. Okay, so all the things are pretty much there. So these are the terms in green color. Okay, so it goes to here, and here. And then the remaining thing is integration of dr from capital R to infinity. Okay, and then here we can see that this integration is like this one is like integration of r to the -2 dr from capital R to infinity. Okay, so this one R to the negative 2 plus 1 will be R to the negative 1 and then divide by negative 1. Okay, so this is the antiderivative. And then evaluate from R to to infinity. When you plug in infinity here, so this is 1 over R, this is negative 1 over R, evaluate from R to infinity. So when you plug in infinity here, this term will be 0. So it becomes 0 minus R plug in here will be negative 1 over R, like this. So it turns out to be 1 over R for this thing. Okay, so this is finally to be 1 over R, like this, 1 over R, like this. Okay, and then okay, so here we can see that it will be let me see. Okay, so this is negative 1 over R. We still have a negative sign in the front. So finally it becomes negative Q over 4 pi epsilon naught and then times 1 over R, like this. And then this negative sign and this negative sign will cancel because this is negative V. So this negative sign and this negative sign cancel. Finally, we have V to be 1 over 4 pi epsilon naught times Q over R. So you need to be very careful about the plus or negative sign, but it turns out to be all for all equation. At the end of this chapter, I will summarize 4 similar equations. All of them are positive, so you don't need to worry about whether it's positive or negative. But when you really want to derive it mathematically in a rigorous way, then you need to be very careful about which part has a negative sign, which part don't, and then finally you should come up with a correct answer. And in the past, someone may have asked why we need to divide this to be I, this to be F, whether we can change it. Let's say this one to be the initial point, this one to be the final point. Okay, and then we can come up with a V minus 0 on the left side. And then usually the student will find that the lower side still have a negative sign, and then it should have a negative sign. But yeah, but I should say that you should be very careful about the plus or negative sign because there are something like the inner product and also this axis. This integration also have the direction because when you learn calculus, it is like fx dx from A to B should be negative from B to A, fx dx. So you need to be very careful to make everything correct. So yeah, of course, even if you make this one I, this one F, you can still get the correct answer. But your mathematics should be good enough to do so. So in the textbook, it just so that this is I, this is F, then it will skip some of the point that will be easy to make mistakes. So actually this one is correct. And then, yeah, so just now, this is the potential due to one charged particle. And then if we have multiple charged particle, then what we need to do is, let me see, I think we just forgot the term. Here it should be a term 1 over 4 pi epsilon naught there. Okay, 1 over 4 pi epsilon naught. Just skip that one. Okay, so here if we have multiple charged particle, the total potential should be the sum of all the potential, all the potential due to different particle. But the point, yeah, so it's somehow similar to what we did before for the total force, total E field, we add them together. But the difference is, before the force is a vector, the E field is a vector. So when we need to add all the force or all the forces or all the electric fields together, then we need to decompose the forces or E field into x-axis component, y-axis component, and then we add the x-axis component together and then add the y-axis component together. But here potential is a scalar field. This is a scalar field. So when we need to add them together, it's just like a algebraic sum, 代数和 of individual potential with no consideration of directions. So it will be the easier part here. Okay, so here we have a quick checkpoint. So it says before the quick checkpoint, we have a highlight. It says positively charged particle produce positive electric potential, and a negatively charged particle produce a negative electric potential. So it is very trivial because the expression is like V equals 1 over 4 pi epsilon naught, and then Q over R. So this one is a positive value. This one is also a positive value. So if Q is positive, this is positive. If Q is negative, V is also negative. So this is very trivial. And this is a checkpoint. So it says the figure shows 3 arrangement of 2 protons, using the red dot to specify. Okay, so rank the arrangement according to the net electric potential produced at point P by protons greatest first. Okay, so 他问你哪一个产生的 potential 最大或者是按顺序排。Okay, so what do you think? Which one is the largest one? So the first one, we have this one here and here. So this is small d, this is large D, this is point P. So we would like to consider VPA, and then this one is VPB, and then for this one, VPC. Okay, so this is small d, this is capital D, this is small d, this is capital D, this is small d, this is capital D. Okay, so which one is the largest one? A, B, or C? Who think A is the largest one? No. B. Okay. C. No. So which one is the largest one? Which one is the largest one? A, B, or C? Okay. 有没有人答案？哪个最大？没有答案，没有答案。那我说了，so actually, the answer is they are the same. VPA equals VPB equals VPZ. So they are actually the same because VPA, VPC, VPB, and VPC, and it's actually like 1 over 4 pi epsilon naught, and then times proton. Proton you consider is E over D, and then plus 1 over 4 pi epsilon naught, and then E over capital D. So all the 3 cases are the same. So you just consider, this is the first one. So this proton generate the potential here correspond to this term, and then for this one correspond to this term. And then, so as I mentioned, the potential is not a vector, it's just a scalar. So it doesn't really matter, this is a 90 degree, this is a 180 degree, so it doesn't really matter. So all the things just need to add the scalar together, and then they are the same things. If you really need to consider, if this is EPA, okay, EPB, and then EPC, okay, EPC, then you can say, the absolute value of EPA will be larger than EPB, and then larger than EPC. Okay. So this one, they will yeah, part of the E field will be cancelled, and then for this one they will be add together. Okay, for this one it's just like the square sum and then take the square root. Okay, so it lies between. Okay, so they are different things. They are different things. For the potential, it would be easier to consider it's just a scalar. Okay, so okay, so here if we have a sample problem. Okay, so here is ask you what is the electric potential at point P, which is actually the center of a square, located at the center of the square, and then the distance d, and then the charge q1, q2, q3, q4. Okay, so this is pretty easy. Okay, so you can see we should first determine what is the distance. All the distance should be the same thing. Let's say this is r. This is r. As much as these are the center point. R. Okay, so r should be d over square root of 2. D over square root of 2. Okay, because all the triangle are right angle triangle, and then so this side equals this side, and then they are also right angle triangle. So yeah, so this is this square plus this square to be this square. So yeah, so r to be d over square root of 2. Okay, so the total v will be nothing but summation of vk, which means that k from 1 to 4. Okay, so which is nothing but k times q1 over r1 plus q2 over r2 plus q3 over r3 plus q4 over r4. Just using the equation here. Okay, so this is actually k. I forgot the term k there. Okay, so it's just like k times q1 over r1, q2 over r2, q3 over r3, q4 over r4. Actually, all the r are nothing but, so this is r1, 2, 3, 4 are all d over square root of 2. So it turns out to be k over d over square root of 2, and then times q1 plus q2 plus q3 plus q4. Okay, then we can just plug in the number. K is 8.99 times 10 to the 9th power, and then d is 1.3 meter, 1.3 over square root of 2, and then q1, q2, q3, q4 plus 12, negative 24 plus 31 plus 17. So 12 minus 24 plus 31 plus 17, and then times nano 10 to negative 9. Okay, so this number is 350 volt, 350 volt. Okay, so yeah, so it already tells you the answer. So 330 volts. Okay, each side they draw the equipotential surface there. Yeah, don't ask me why the shape will be like that. Okay, if you really need to know, then you probably need a computer software to do so. You probably need a computer software to do so. You try to let's say you have for example, this is the coordinate axis, and then you just assume this is let's say this is d over 2, and then this is negative d over 2, so on and so forth. You define this is q1, q2, q3, and q4, and then you try to calculate the potential over the whole space, and then you try to connect the point with similar potential. Then you will draw some equipotential surface. It might be difficult, but yeah, that's the point. Of course, there may be some computer software to do so, but at least you can imagine Q1, Q3, and Q4, they are positive charge. They are positive charge. This is negative. So at least we can know that the equipotential surface should somehow like circle the positive charge, isolating the negative charge. Okay, so next we have another sample problem. So it says 12 electrons of charge negative E are equally spaced and fixed around a circle of radius r relative to V equals 0 at infinity. What are the electric potential and electric field at the center C of the circle due to these electrons? Okay, so this is really easy. I just leave so little space. So V is nothing but K times all are negative E, and then we have 12 of them, so which is nothing but a negative 12E over, this is a circle, so all the distance will be capital R. So nothing, so this is, yeah, that's it. And then for part B, it asks you if the electrons are moved along the circle until they are non-uniformly spaced over 120 arc. Okay, so like this one. Okay, what then is the potential at C? How does the electric field at C change? Okay, so answer the first question first. So yeah, the potential at C. The potential at C is like nothing change because it is just a scalar sum. So yeah, as much as the charge doesn't change, the distance doesn't change, then V should be K times negative 12E and then over capital R. So the V doesn't change doesn't change at all. Doesn't change. But it asks you what then the potential, the electric field. How does the electric field at C change, if at all? So for the first one, you can imagine the E field will be symmetric. For this one, it will generate E field pointing upward. For this one, it will pointing downward with the same magnitude. So all the E field will cancel each other, which means that for this one, EA will be 0. But for EB, it is not 0 anymore because they cannot cancel because they are concentrated at this side. So you can imagine this one points to this side, this one points to this side, this one points to this side, so on and so forth. So you can imagine the E field will point to around this side. So this will be EB. This will be EB. It won't be 0 because they have no possibility to cancel this component. Okay. Okay, so this sample just show you electric potential is easy to calculate. Okay, so next we have another case called potential due to electric dipole. So in chapter 22, we already derived the electric field due to an electric dipole along the z-axis only. At that time, when you calculate the E field generated by the electric dipole, we can only come up with the expression on the z-axis. But here, this is not the case. We can actually come up with the expression with in the whole space. Okay, so let's see how we can come up with the expression. Okay, so here we have two charges. So we have two terms. V equals V plus V minus. Now, V plus is the potential generated at the point P due to the positive charge. And then V minus is the electric potential generated at point P due to the negative charge. Okay, so it is nothing but 1 over 4 pi epsilon naught. This is K times Q. Okay, as an electric dipole, they should have a opposite sign of charges with same magnitude. So one is positive q, one is negative q. And then the distance from the positive charge to point P is r plus. So we have r plus here. And the distance from the negative charge to point P is r minus. Okay, so we have q over r plus, negative q over r minus. Okay, so we can just add them together. So of course r plus and r minus are so close, but we cannot make it like r plus is similar to r minus is similar to r, and then you will just cancel all the thing, and then it turns out to be 0. So that's not good enough. So we try to do some calculation before we try to do the approximation. Okay, so we add them together. So this is the common factor, r plus times r minus. So and then q is a common factor. We can just factor it out. So we have q over 4 pi epsilon naught in the front, and then it turns out to be 1 over r plus minus 1 over r minus. So it will be r plus r minus, and then r minus minus r plus. Okay, still we cannot apply the approximation yet because it turns out to be 0. Here we try to do the approximation like this. So let's see. This is the original graph. This is the approximate graph. Here we also assume that this point P is very, very far away. Usually, we also have the far field condition here. So it's just like, suppose you have a mobile phone, it should have an antenna. Yeah, of course, nowadays the antenna is not like a long bar. Okay, it's like a coil. Okay, if you check on my YouTube video, like 8 years ago, I have record a video about the antenna of a mobile phone. So yeah, if you have interest, you can just check it out. But of course, I just commentated in Cantonese. So yeah, if you only know Chinese, then you may not be able to understand. But actually, it's just like an antenna. You like to communicate with the base station. So the base station should be far away enough so that you can use the far field condition usually. Okay, so so here we try to have this far field condition, and in that case we can consider this line and this line are parallel. Just like when you learn the optics in high school physics. Just like the light source is infinitely far away, like the sun, and then you will consider the ray are parallel. So as much as this one is very, very far away, then we can consider this is P, this is also P, and then these two lines are parallel to each other. Okay, just hard to imagine, but yeah, that's the case. Okay, so this is r plus, this is r minus. So when we try to subtract them, okay, of course they should something like that rather than that one. This is P, this is P. Okay, this is r plus, this is r minus. So r minus minus r plus should be this one. Okay, so we have r minus minus r plus. Okay, so here d is the distance between the dipole, the two charges, between the two charges. So this is d, and then we also have the angle. Theta. Okay, so originally this point connecting with the point P we concern, and then this angle is called theta. Okay, now as much as we assume P is infinitely far away, we also assume this is theta, this is also theta, as much as they are parallel to each other. Okay, so in that case, this line this line will be d times cosine of theta. So we have r plus r minus r plus is d times cosine omega. So here we have the far field condition here, and then r plus times r minus, we can just approximate them to be r only. Okay, so both of them are r. Then we can just plug in this one to here, this one to there. Okay, then we will have v equals q over 4 pi epsilon naught d cosine of theta, and then r squared, and then r squared. Okay, and then we can just collect the term. This is q, this is d. If you still remember, for the electric dipole moment, p should be q times d. So it turns out to be p times cosine of theta, r squared, then times 1 over 4 pi epsilon naught. So this is interesting. So just now I mentioned the video on my YouTube channel, and at that time I also mentioned that when you use a mobile phone, there should be a direction that has a stronger ability to transmit and receive. Okay, for this one, this side will have a stronger ability to receive or transmit. So sometimes when you have when your signal is weak, you can try to point your mobile phone to the router or the base station. Then you will make the signal you receive to be stronger, and usually this direction will be weak, and also it will try to design that this direction is also weak, because when you try to talk with your phone, usually like this, you don't want too much EM wave to emit to your body, because there are energy. It may affect your health. So they will try to avoid this thing. Okay. So yeah, if you use this sign point to that router, maybe you can still receive, because there will be some refraction. But if you want your signal to be faster, then try to point. then the signal will be stronger. But of course, if it is so close, then yeah, it's not that different. Not much. There will be not much difference. But yeah, at least for some of the case, if you are quite far away from it, then you can try to do so. And also, I think I also mentioned the 2.4 gigahertz Wi-Fi and also the 5 gigahertz Wi-Fi. There are different for some physical characteristic. The 2.4 gigahertz Wi-Fi have the stronger ability to propagate for farther distance. So yeah, so for the 5 gigahertz Wi-Fi signal, it will attenuate faster. OK， 就是2.4G 的那个 WiFi signal 的话，就是它有能力可以传达得更远。然后5GHz 的 signal 的话，就是它比较快会衰减，所以5GHz 它如果它最高速会比较快，但是前提是你看得到那个 router。如果你离它很远的话，你就会收讯很差，然后就会觉得很慢。那如果很远的话，那反而就是连2.4G 的的 signal 会比较好，因为它有能力传得更远。对，你至少确保一个比较大的那个 signal strength。Okay, so here we talk about the potential due to a continuous charge distribution. Okay, so just similar to before. So if we have continuous charge distribution, we try to cut it into small pieces, and then we try to have dV for everyone, and then we try to add them together. But this one, we don't need to consider about the direction, so we just need to add them together using the integral. So usually it will be more easy. Okay, and the equation is just like the total v is the dv and the integration, just like add all the dv together. And then the dv, just now v is 1 over 4 pi epsilon naught times q over r. So here we just add this one on. dv is generated by dq. Okay, for example, if we have a sphere with a continuous charge distribution, okay, and then we consider this part has dq, will generate the dv at this part, and then we integrate all the things. So we have a dq. So we just put this one to here. Then we have a dq over dr. Usually r is related to q, so we just leave this one inside. And then of course this is a 1 over 4 pi epsilon naught is a constant, so we just put it outside. So the expression is like this. So here we try to come up with the expression for two situations. The first one is a line of charge. So here we assume that we have a bar with the length capital L, and then we try to come up with the potential at point P. So yeah, so here, so this is the starting end, and then perpendicular to it, we find a point P. We try to find a VP. What is VP? Or here we only denote it as V. Okay, so yeah, so of course this is not, yeah, for example, for this part and that part, okay, of course the charge is uniform distributed, so dq is uniform, but the distance are not the same. So for this one, r is smaller. For that one, r is larger. Okay, so I mean dq over r are not uniform, so we need to use the integration to do so. So first, we have dq in this formula. We need to change it to a variable dx, so that we can integrate from, just say, 0 to capital L to do the integration. So we need this change of variable. dq equals lambda dx. Lambda is the linear charge density as before. Linear charge density. Okay, as before. Okay, so we have a dv equals 1 over 4 pi epsilon naught times dq over r. Then we can just plug in this one into here. So dq is lambda dx. And then for r is not an integrated variable. So we try to express this r in terms of x and some other constant variable. So in this case, we know that this distance, the distance here is d. And for example, this one will be like x. This one will be like x, or you can just look at this figure. This is x. This is the dx, and then this is d. So r, according to the Pythagorean theorem, will be d squared plus x squared, and then take the square root like this. So r equals x squared plus d squared square root. Okay, we have this expression. So now we can start the integration, because this is dx, and then the whole expression only consists of variable x. All other variables are constant. D is constant, lambda are constant, this is constant. So we can start the integration. V equals integration of dv, and then we just plug in this expression here. So we have a lambda over 4 pi epsilon naught here. And then we have dx over this square root. So this square root, 1 over this square root is like negative 1/2 power, like this. Okay, and then according to appendix E, the expression is like this. But just let you know how to use the calculus to find this integral. So let's see. So this integral will be equal to that one. So let's start. Okay, so when we come up with this one, x squared plus a constant square inside a square root, we always assume that x to be d times tangent of theta, so that x squared plus d squared will be like d squared and then 1 plus tangent square theta, which will be d squared secant square theta. And then we also have dx to be d secant square theta d theta. Okay, so take the derivative of tangent theta will become secant square theta. And then as much as we have a change of variable, originally this is dx from 0 to L, we need to find the corresponding lower and upper bound after changing the variable. So this is like, let me see, x over d is the tangent of theta. So this is theta. And then this is d squared plus x squared, and then take the square root. Okay, so when x is 0, this theta should be 0. So this integral 0 to L, and then x squared plus d squared, and then negative 1/2 dx. So the lower bound will be 0 when x is 0, and then 0 over d to be tangent of theta L. So this theta L will be 0 because this is 0. And for the upper bound, let's say this is 0. Okay, so this will be 0. And then when x to be capital L, L over d will be tangent of theta L. So we just call this one theta L, but keep in mind that we have this expression. And then for the following, okay, we have this one. X squared plus d squared will be this one. So we take the square root, so it becomes d times secant theta, and then negative 1. So we put it to the denominator, d times secant of theta. And then dx is this one. So we have d secant square theta d theta. Okay, so d and d cancel, square and this one cancel. So it becomes integration of 0 to theta L, secant theta d theta. Okay, so a trick here is to multiply and divide tangent theta plus secant theta once. Okay, tangent theta plus secant square, secant theta d theta. Okay, this is a trick, so you need to remember it. So secant theta tangent theta will be the derivative of secant theta, and then secant theta times tangent theta will be the derivative of a secant theta. Okay, and then secant theta squared will be the derivative of tangent theta. So it becomes 0 theta L, and then d. Let's write it as a tangent theta plus secant theta, and then we have a tangent theta plus secant theta. Okay, so this is like you can regard this one is u, this is u, so it becomes a lateral log. So it becomes lateral log of tangent theta plus secant theta, evaluate from 0 to theta L, like this. Okay, so this is 0, and then that one is theta. Okay, so here we can see tangent theta L will be L over d. So we have L over d, and then secant theta will be this one over this one, will be plus square root of d squared plus L squared over d. Okay, and then minus natural log of plug in 0 there, tangent of 0 will be 0, and then secant of 0 will be 1, natural log of 1, this one will be 0. So finally, the answer will be natural log of L plus, let's say L squared plus D squared, and then take the square root all over D, like this. So we get this expression. So that's why the expression here look like this, using the appendix. Okay, so this is for the line of charge. We will be able to find the potential at point P with a variable D. So yeah, so no matter how far it is, you will be able to find with this expression. Okay, so yeah. Okay, so let us stop here today.